On a sunny afternoon in 1950 at Los Alamos National Laboratory, a small group of scientists were walking to lunch. They were talking casually about UFO sightings and recent advancements in space exploration. Among them was Enrico Fermi, the Nobel Prize-winning physicist who had worked on the Manhattan Project. The group discussed how, given the vast number of stars in our galaxy, it seemed statistically inevitable that intelligent life should exist somewhere else. After all, the Milky Way is home to over 100 billion stars, many of which are older than our Sun, and we now know that most stars have planets. If life arose quickly on Earth, why shouldn't it have done so elsewhere, possibly billions of years before us? Fermi listened, deep in thought. Then, as they approached the cafeteria, he suddenly stopped and blurted out a simple but world-shaking question. Where is everybody? It was a question so deceptively simple, yet it sliced through layers of assumption and optimism. In that moment, the Fermi paradox, the puzzling contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it, was born. What made this question so profound wasn't just that it asked about aliens, but that it forced scientists to face a logical contradiction. If intelligent civilizations are common, why have we never seen any sign of them? Why no spacecraft, no probes, no signals? Fermi's lunchroom query has since become one of the deepest mysteries in science, haunting astronomers, philosophers, and science fiction writers for over 70 years. To grasp why Fermi's question matters, we need to understand the sheer scale of the playing field. The Milky Way isn't just big, it's mind-bogglingly vast. Imagine traveling at the speed of light, 300,000 kilometers per second, and still taking about 100,000 years to cross the galaxy from one side to the other. Inside this cosmic disk are an estimated 100 to 400 billion stars, and modern astronomy suggests that planets are not rare. In fact, there may be more planets than stars. Recent discoveries by NASA's Kepler mission have revealed thousands of exoplanets, some within the so-called habitable zone, the region around a star where conditions might allow liquid water to exist. Statistically, there could be tens of billions of Earth-like worlds in our galaxy alone. And if you extend this thinking beyond the Milky Way to the observable universe, which contains at least 2 trillion galaxies, the numbers explode into incomprehensible territory. This is why scientists are so confident that we're not unique, at least statistically. With such an enormous number of potentially habitable planets, the odds of life developing somewhere else seem overwhelmingly high. And yet, despite this staggering abundance, our skies remain silent. We've scanned for decades, listening for radio signals, searching for strange anomalies, and exploring our solar system for evidence of visitors, and we've found nothing conclusive. This tension between probability and observation is exactly the heart of the Fermi paradox. Fermi's reasoning wasn't based on some mystical feeling, it was cold, mathematical logic. If the galaxy is old and full of planets, then intelligent civilizations, given enough time, should have emerged long before humans did. Even with slower-than-light travel, an advanced civilization could colonize the entire Milky Way in just a few million years, a blink of an eye in cosmic terms. They wouldn't have to send vast fleets of starships all at once. Self-replicating probes could do the job, hopping from star to star, building new copies of themselves, and spreading exponentially. This is sometimes called the galactic colonization hypothesis. Once such expansion begins, it's extremely hard to stop, unless every civilization chooses not to spread or all mysteriously self-destruct. So here's the contradiction. If civilizations arise often, then at least one should have had the time to fill the galaxy with their presence, technology, or even ruins. But when we look around, with telescopes, radio arrays, and spacecraft, we see no such signs. The paradox is essentially this: if life is common, then aliens should be here by now. If they're not here, maybe life is rare. Both possibilities are equally astonishing, and both challenge our understanding of our place in the universe. One of the simplest ways to estimate the likelihood of extraterrestrial civilizations is through the Drake equation, proposed in 1961 by Frank Drake. It multiplies together a series of probabilities: the rate of star formation, the fraction of stars with planets, the fraction of those planets that are habitable, the fraction where life actually emerges, the fraction of life that becomes intelligent, and the fraction that develops technology capable of communication. The final factor is how long such civilizations survive before disappearing. Plug in optimistic numbers, and you might get thousands of civilizations existing right now in the Milky Way. Plug in pessimistic numbers, and you might get only one: us. The Drake equation doesn't give a final answer. Instead, it frames the problem. What's unsettling is that many of these factors are still unknown. We now have good data for the first few. Planets are everywhere. But the later factors, like the probability of life forming or intelligence evolving, are still complete mysteries. The more we learn about planets, the more it seems that the answer to the paradox lies in the biology. Maybe life is incredibly hard to start, or perhaps intelligence is an evolutionary fluke. Astronomers sometimes call it the Great Silence, the eerie absence of detectable signals or evidence of extraterrestrial civilizations. In the 1960s, projects like SETI, Search for Extraterrestrial Intelligence, began scanning the skies for radio transmissions that might be artificial in origin. Decades later, despite vastly more sensitive equipment, the result remains the same. We've looked at thousands of nearby stars, listened across multiple frequencies, and even searched for laser flashes or unusual energy patterns. Nothing. Some scientists argue that our search has barely scratched the surface. The radio spectrum is vast, and we've only listened to a small portion for a short period of time. Others say that if advanced civilizations were common, even a tiny percentage of them should have been detectable by now. The silence isn't just absence, it's a constant reminder that we might be more alone than we'd like to believe, or that something is keeping civilizations from reaching out. Perhaps a universal fear, a technological limit, or something far more unsettling. One possible solution to the paradox is the zoo hypothesis, the idea that advanced civilizations know we're here but choose not to contact us, much like zookeepers observing animals without interfering. In this scenario, Earth might be under a kind of quarantine, intentionally isolated so our natural development isn't disrupted. This would require a civilization or a coalition of civilizations capable of enforcing such a rule across the galaxy. If true, it would explain why the universe seems empty despite possibly being full of life. The silence is deliberate. The zoo hypothesis also taps into our own history. When technologically advanced societies have encountered less advanced ones on Earth, the results have often been disastrous for the latter. Perhaps aliens have learned this lesson and avoid repeating it. The downside is that this hypothesis is almost impossible to prove, because if such a civilization wanted to hide from us, they could easily do so. Still, it's a favorite among science fiction fans because it implies the galaxy might be alive with watchers, patiently waiting for humanity to reach some milestone before making contact. The rare Earth hypothesis offers a more sobering answer. Maybe we're alone because complex life is extremely rare. While microbial life might be common in the universe, the leap from simple cells to complex intelligent organisms could be extraordinarily difficult. Earth's own history supports this. For most of its 4.5 billion year existence, life was microscopic. Complex life only appeared in the last 600 million years, and humans have existed for a mere fraction of that. The rare Earth idea points to a series of perfect conditions on our planet: a stable climate, a large moon that stabilizes our tilt, plate tectonics that recycle nutrients, a protective magnetic field, and the right kind of star. If even one of these is missing, complex life might never emerge. In other words, the galaxy could be teeming with bacteria but devoid of civilizations. This possibility makes the Fermi paradox even more poignant. We might be one of the few, or even the only, intelligent species in our galaxy. The Great Filter is one of the most chilling explanations. It suggests that at some point between the formation of a habitable planet and the rise of a galaxy-spanning civilization, there's a nearly impossible hurdle, a filter that almost no species can pass. This filter could be behind us, meaning life rarely gets as far as humans have. or ahead of us, meaning civilizations like ours almost always destroy themselves before colonizing space. If the filter is behind us, we might be incredibly lucky, one of the few to survive it. If it's ahead, it could be something like nuclear war, climate collapse, artificial intelligence gone wrong, or unforeseen cosmic dangers. The Great Filter forces us to look at our own survival in a new light. If we don't see aliens, maybe it's because they all fail to survive their own technological adolescence. That possibility should be a warning, not just a curiosity. Some argue that the paradox isn't a paradox at all, because aliens are already here. This idea is often linked with UFO sightings and claims of extraterrestrial visitation. While mainstream science finds no credible, verifiable evidence of alien contact, the idea persists in popular culture. Proponents argue that aliens could be here in forms we can't recognize: microscopic machines, energy-based life, or even species living in the deep oceans or underground. Others suggest that ancient astronaut theories might hold some truth, with civilizations having visited Earth in the distant past and either left or blended in. The challenge with this idea is evidence. Extraordinary claims require extraordinary proof, and so far, nothing has withstood rigorous scientific scrutiny. Still, if aliens were skilled enough to travel between stars, they would likely be skilled enough to hide completely if they chose. Another possibility is that we're simply using the wrong methods to search. Most SETI efforts focus on radio signals because they travel well across space. But who's to say aliens use radio at all? Advanced civilizations might use communication methods far beyond our understanding: quantum entanglement, neutrino beams, or something we can't even imagine. It's also possible they communicate in ways that blend with natural cosmic noise, making their messages indistinguishable from background radiation. Our own communication technology has shifted rapidly. Within a century, humanity has gone from Morse code to fiber optics to encrypted digital signals that are much harder to detect from afar. If aliens have made similar transitions, the window during which their signals would be detectable might be extremely brief. In short, the universe could be buzzing with messages. We just don't have the ears to hear them. One explanation that doesn't require aliens to be hiding or extinct is the time gap problem, the idea that civilizations might rarely exist at the same time. The universe is 13.8 billion years old, and the Milky Way formed over 13 billion years ago. In that time, countless stars and planets have formed and died. It's entirely possible that civilizations rise and fall on cosmic timescales that barely overlap. Imagine if an alien civilization had thrived 500 million years ago, built wonders beyond our imagination, and then disappeared. Their cities crumbling to dust, their signals long faded into the cosmic background. By the time humans evolved, their presence would be undetectable. Similarly, we might be early or late compared to the galactic average. If intelligent life tends to emerge in clusters separated by millions of years, the odds of two civilizations meeting are incredibly small. In this view, the galaxy might be filled with the ghosts of civilizations past, a silent graveyard of once thriving worlds, each existing too briefly to overlap with the others. The paradox, then, isn't that we're alone, it's that we're isolated by time itself. Popularized by science fiction author Lou Cixin in the Three-Body Problem trilogy, the Dark Forest theory offers a more ominous explanation. It likens the universe to a dark forest, where every civilization is a hunter with a gun, silently hiding among the trees. In this forest, any civilization that reveals its position risks being destroyed by others. The reasoning is simple but chilling. You can't know the intentions of another species, and by the time you find out, it may be too late. So the safest move is to stay silent, or to eliminate potential threats before they eliminate you. Applied to the Fermi paradox, this suggests that advanced civilizations intentionally avoid broadcasting their presence, and any that do are quickly removed by others. This could explain the Great Silence. The galaxy might be full of life, but all are whispering in fear, hoping not to be noticed. If the dark forest theory is correct, then our own radio broadcasts of the past century might be akin to shouting in a dangerous jungle, a risk we took without fully understanding the consequences. Perhaps the most tragic solution to the paradox is that civilizations tend to destroy themselves before they can spread among the stars. The more technologically advanced a society becomes, the more powerful its ability to harm itself. On Earth, we've seen this in the form of nuclear weapons, environmental destruction, and the rise of potentially uncontrollable artificial intelligence. The civilizational trap theory argues that intelligence comes with self-destructive tendencies, political conflicts, resource exploitation, and short-term thinking. If most civilizations burn out within a few centuries of becoming technologically capable, the galaxy could be littered with the ruins of those who came before us. The silence we hear might not be from lack of life, but from the near-universal inability to survive long enough to become a multi-planet species. In this scenario, our future hangs in a delicate balance. We might be on the brink of either extinction or the rare breakthrough that allows us to survive. As we've discovered more exoplanets, scientists have realized that many potentially habitable worlds might actually be ocean planets, worlds covered entirely by deep global oceans. While water is essential for life as we know it, an all-ocean world poses challenges for the development of technology. Without land, there are no fires, no metallurgy, and no easy way to develop industrial civilization. Intelligent life could arise in the seas, but without the ability to manipulate fire or build complex machinery, they might never create a space program. The galaxy could be full of intelligent but trapped civilizations, aquatic beings gazing up at the stars without any way to reach them. If true, this would mean that the kind of mixed land and sea planet Earth represents is much rarer and more crucial for spacefaring than we thought. Even if civilizations do exist and have the capability to communicate, they might choose not to because it's not worth the effort. Interstellar communication is incredibly resource-intensive. Sending powerful, targeted signals over light years requires enormous energy and patience. The response might not arrive for centuries. Civilizations may prefer to invest in local exploration or technology that benefits their own species rather than broadcasting into the void. From their perspective, contacting us might be as low priority as sending a message in a bottle into the ocean is for us, a romantic but impractical gesture. This explanation doesn't require fear, malice, or rarity, just pragmatism. If everyone decides it's not worth the cost, the galaxy naturally becomes a quiet place. We tend to imagine aliens as versions of ourselves, humanoid, carbon-based, oxygen-breathing, with technology that's at least somewhat familiar. But what if life elsewhere evolved along completely different lines? They might be silicon-based, live in gas clouds, or exist as patterns of electromagnetic fields. Their technology could be biological, chemical, or something beyond our concepts of engineering. In such cases, their signals, structures, or behavior might blend into the natural phenomena we already observe. We might have already detected alien activity, we just didn't recognize it for what it was. This too alien to recognize hypothesis forces us to confront our own anthropocentric bias. The universe might be teeming with life that is as incomprehensible to us as our smartphones would be to a trilobite. The early arrival hypothesis suggests that intelligent life is just starting to emerge in the universe, and we're among the first. Stars like our Sun are relatively young compared to the oldest stars in the galaxy, and habitable planets may only have become common in recent cosmic history. It's possible that the chemical elements necessary for complex life, heavy metals for instance, took billions of years to build up through generations of supernovae. If that's the case, then the galaxy might currently be in its childhood stage, with civilizations only beginning to appear. In a few 100 million years, the stars could be alive with radio chatter and starships, but right now, we're just early to the party. The history of Earth shows that life is vulnerable to mass extinction events, asteroid impacts, supervolcano eruptions, gamma-ray bursts, and even sudden climate shifts. These can wipe out entire ecosystems in the blink of an eye. If such disasters are common across the galaxy, then civilizations might be repeatedly reset before they can reach advanced stages. Imagine a world where intelligent life arises, builds cities, begins exploring space, and then an asteroid the size of Mount Everest slams into it, ending everything. The survivors, if any, might be pushed back to a pre-technological state, forced to start over from scratch. Over billions of years, this cycle could prevent most civilizations from ever surviving long enough to make their presence known. A more philosophical and mind-bending answer is the simulation hypothesis. The idea that our entire universe is a kind of advanced computer simulation created by some higher intelligence. If that's the case, the reason we don't see aliens could be simple. The simulation doesn't include them. They weren't programmed into our reality, perhaps to focus on our species or to simplify computational requirements. While this sounds like science fiction, some physicists and philosophers argue it's worth considering, especially given the growing sophistication of our own simulated environments. If we are in a simulation, the Fermi paradox might not be a cosmic puzzle at all, just a design choice. Lastly, some scientists suggest that the galaxy might simply be a cosmic wilderness, a vast, largely empty space where intelligent life is scattered so sparsely that contact is virtually impossible. Imagine a forest where each tree is separated by hundreds of miles. Even if birds live in those trees, they might never hear or see each other. In such a scenario, civilizations might exist, but the distances, time delays, and vast emptiness make meaningful interaction a near impossibility. This isn't due to danger, rarity, or choice, just the sheer geometry of the galaxy. If this is the case, then our search for extraterrestrial intelligence might be less about finding neighbors and more about proving that we are not completely alone in the cosmic wilderness. The laws of physics, as we currently understand them, place a hard limit on how fast anything can travel, the speed of light. This isn't just an engineering challenge, it's a fundamental rule of the universe. Even at 99.9% of light speed, reaching the nearest star system, Proxima Centauri, would take over 4 years. Crossing the galaxy would take tens of thousands of years. For an interstellar civilization, this means expansion is slow, expensive, and potentially risky. While science fiction often imagines faster-than-light drives, wormholes, or hyperspace lanes, no credible evidence suggests these are possible within our physics. So maybe advanced civilizations do exist, they just can't or won't traverse the immense distances between stars. They might prefer to focus on colonizing their own star systems, sending probes rather than people, or expanding digitally rather than physically. If light speed truly is an unbreakable barrier, then perhaps the galaxy will always remain a patchwork of isolated civilizations, each trapped in its own bubble of stars. Another possibility is that advanced civilizations eventually lose interest in the physical universe. Once they develop highly advanced virtual realities, nanotechnology, or mind uploading, they may retreat into digital worlds of their own making. Why risk the dangers of interstellar travel when you can create an infinite paradise inside your own computer systems? This inward turn hypothesis suggests that after reaching a certain level of technology, civilizations stop leaving traces in the physical universe because they no longer interact with it in large-scale ways. From the outside, such a civilization might appear to vanish, leaving behind only the natural light of its star. This could mean that the galaxy is full of advanced beings, but they're all living in self-made digital heavens, disconnected from the rest of reality. For us, that would mean the silence isn't because they're gone, but because they've gone elsewhere. Civilizations that expand technologically face ever-growing energy needs. On Earth, we've already tapped into vast reserves of fossil fuels, nuclear power, and renewables, but our energy consumption is tiny compared to the potential of a whole planet, let alone a star. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale of civilizations based on their energy use. Type 1 harnesses all energy from their planet. Type 2 harnesses all energy from their star, and Type 3 harnesses all energy from their galaxy. The problem is that reaching higher types may require monumental engineering projects, like Dyson spheres, enormous structures built around stars. If such megastructures existed in our galaxy, we might expect to detect them by their heat signatures, but so far, surveys have found nothing conclusive. Perhaps most civilizations never managed to solve the problems of sustainable energy before collapsing, or perhaps those who do intentionally limit their growth to avoid catastrophic risks. One assumption behind the Fermi paradox is that intelligence naturally leads to technological expansion. But what if that's a human bias? On Earth, plenty of intelligent species, dolphins, octopuses, certain birds, show problem-solving skills, communication, and even tool use. Yet they haven't built cities or spaceships. A civilization might be highly intelligent, yet lack the cultural drive for exploration. Or they might have a philosophy that values harmony with nature over technological conquest. We imagine aliens as driven to explore because we are curious, restless, and ambitious, but perhaps we're the outliers. If most intelligent life is content to remain in its local environment, then the galaxy could be full of smart species who simply never attempt interstellar travel or large-scale communication. It's possible that civilizations are all around us that have blended so seamlessly with their environments that we can't distinguish them from nature itself. This idea, sometimes called the camouflage hypothesis, suggests that an advanced species could manipulate matter and energy so subtly that its presence becomes indistinguishable from the background noise of the universe. They might exist as networks of microscopic machines, clouds of self-replicating nanobots, or bioengineered ecosystems that look like untouched wilderness. In this scenario, every lush alien jungle or stable planetary climate we observe could be the result of deliberate design, but we'd never know unless we stumbled across undeniable evidence. If they've chosen such a hidden existence, it might be for security, ethics, or sheer aesthetic preference. Consider this unsettling possibility. Civilizations might not just rise and fall, they might leave. Once a species masters technology beyond our comprehension, they could abandon the physical galaxy entirely. This might mean migrating to other universes if multiverse travel is possible, or existing in entirely different dimensions or energy states. From our perspective, they would simply vanish, leaving no trace but natural starlight. If this is common, then the reason we don't see galactic empires is that advanced civilizations have already passed through this phase change and moved on to realms of existence we can't perceive or interact with. Perhaps we haven't been contacted yet because the galaxy operates on a principle of wait until they're ready. This could be tied to the zoo hypothesis, but with a more optimistic twist, that there's a threshold of development, ethics, or stability a civilization must reach before being welcomed into the wider community. From our current perspective, it might feel like we're alone, but from theirs, we're just in a probationary period. They could be monitoring our progress, watching to see if we can avoid destroying ourselves. If we pass the test, first contact might not come in the form of radio signals, but a deliberate, unmistakable appearance, an event so carefully timed that it reshapes our understanding of our place in the cosmos. It's possible that contact has already been made, but we didn't recognize it. This could mean alien messages are encoded in ways we can't interpret, embedded in cosmic phenomena, or even in our biology. Some speculative thinkers have wondered whether the structure of DNA itself could contain a kind of message from an ancient civilization, seeded across the galaxy through panspermia. Others suggest that patterns in cosmic microwave background radiation or pulsar timings could be intentional signals. If aliens have tried to communicate in a way they thought would be obvious, but it relies on concepts we don't yet grasp, then the message could be right in front of us, waiting for the moment we have the knowledge to decode it. One of the most provocative possibilities is that humanity itself might not have originated on Earth. Perhaps our ancestors were seeded here long ago, by another civilization, intentionally or by accident. This would make us the aliens we've been searching for, just without the memory of our true origins. This idea connects to theories of panspermia, where life spreads between planets via asteroids, comets, or spacecraft. If our genetic code carries traces of extraterrestrial influence, it would mean that intelligent life in the galaxy has already reached us, and we are its descendants. The paradox then becomes less about where are they, and more about when will we remember who we are. And then there's the possibility that unsettles many and comforts a few. Maybe we truly are alone. Maybe the chain of events that led to intelligent life on Earth is so vanishingly improbable that it has never happened anywhere else in the galaxy or even the universe. If that's the case, then we are the first, the only, and possibly the last intelligent species in existence. That would make us unimaginably precious, the sole consciousness able to look out at the stars and wonder. The responsibility would be enormous, to survive, to thrive, and to carry the light of intelligence into the darkness, not just for ourselves, but for the universe itself. In that sense, the Fermi paradox is not just a question about aliens, it's a mirror held up to humanity, asking what kind of future we will choose in the silent vastness of space.